Welcome back, everyone. Today we're continuing our series on steel design, and this video is all about block shear. Block shear is going to be some combination of shear failures with tension failures. So let's take this double angle again and let's put it into tension. Now, if I look at my tension failures, I could have a gross section yield out here where my total cross-section area has a stress that's greater than yielding. When I hit a stress concentration, I could also have a net section rupture. So here's where I have net section rupture. But then if I look at block shear, we could have, for example, failure along this entire line of bolts right here. And then I could break down to the edge right there. So what we'll notice with that is if I put my forces in here, my forces are pulling it this way, and I'm going to have a reaction going in the opposite direction, so that we can see that this line here is effectively in a shear stress situation, whereas this small section kind of looks like a net section rupture, just on a smaller area. So this is going to be a tension region right here. So this combination of shear and tension is going to result in this block shear failure. And because of that combination, you could also have it in shear type connections. So if we look at a beam connection, for example, here's a beam connection. I have some load acting down on my beam, and this girder is going to be providing a reaction here. So if I break this up and I look at my two components, if I look at my beam first, the reaction is going to be going through my 3 bolts, and we could have a block shear failure along this line and then up through all of my bolt holes, where this is going to be in tension. And then I have a shear side right over here. Now that's all going to get reversed if I look at, for example, the connecting angle or plate or whatever happens to be connecting my beam to my girder. I'll have a reaction here, and I have force coming down through each of the bolts. So therefore, if I draw my block shear failure, I'm going to see it goes out to the edge right there and down through all my bolt holes. So this is going to be in tension, getting pulled apart. And then I'm going to have shear along this line. Now, one key to drawing these block shear failures is essentially we have to draw something that separates our two pieces that we're trying to connect together. So that gets a little bit more complicated sometimes if we have more bolts. The block shear failure is not always going to go through every bolt that we have. So here is another tension connection. Let's say it's being pulled apart in this manner, and I have this T-shaped section on top. That's this guy right here. That's bolted into a plate. So our plate is this section below it. So if we look at the plate first, if I have a block shear, it is possible to go through all the bolt holes right here and right here. And then I need to totally separate my two pieces, which means this would make sense. I'm going to have this sort of U-shaped section that gets pulled away and separated from the rest of my section. So once again, I'll have a tension region right here. And I have now 2 shear paths, one on top and one down here below. However, there's another tension path that I could have chosen. So for example, what if I had the same kind of shear paths, both of them going here, but then I break my tension path to the edge? Turns out that's also going to totally separate the pieces. I'm going to have this shape right here, sort of a T shape, that will then get pulled away, and this thing will have a full failure. So let's just label those. Let's say the red one is 1 and the blue one is 2. And I'm going to draw a third possibility in green here with 3. We don't need to draw this path through all the bolts to actually separate the two pieces. So let's say I draw it only through one line of bolts. And then I draw that down to the bottom edge. So now I have this sort of L-shaped section that can get pulled away. There's 3 bolts there that are still attached, but this plate is just broken off, and so it's not really going anywhere. And that would have less shear because I only have 1 shear path, but more tension because now my tension path is a much longer distance. The mirror of 3, obviously I could go through the bottom 3 bolts and up to the top. That'll look the same for most symmetric sections, so I'm not going to call that a different path. But if you have sections that are asymmetric, you might have to check both of those. So this could be different from this, for example. Now let's look at that T. You can imagine we could have all the similar shapes, but in reality, we're probably only going to have to check one of these, and that is the path 2 that I drew that breaks out to the edges. And the reason that happens is I have a lot of extra tension area right here in the middle. So this large stem is going to give me a lot of tensile capacity. It's going to be much easier to break off this small area, for example, than this comparatively large area. And so that almost always happens if you have a stem, a web, a stiffener, or something like that. That's a good way of trying to prevent these kind of block shear failures, is to add a lot of tension area where you don't want that block shear to happen. Now that we have some block shear paths, let's look at the capacity using the specifications. So we're going to be looking at specification chapter J, specifically equation J4-5. So this is in the chapter of connecting elements, because again, it's going to be a mixture of shear and tension, so you're neither going to find it in the shear section nor the tension section. And being a combination of shear and tension, we're going to have shear terms here. This one's shear, and this one is also shear. And you could have tension terms. So we could have a tension term here, or a tension term right here. Now let's get out of the way this less than or equal to sign. What does that mean? Well, when the specifications use this less than or equal to sign, they don't literally mean that this has to be less than this. Really, they're talking about you should pick the minimum of two different numbers. So you'll calculate this number. You'll also calculate this number. And the minimum of those two is then going to be your controlling block shear capacity for that particular path that you're looking at. So now let's look at each of the terms in this equation. In the first part of it, both of these, this one and this one, are both rupture cases. And the reason we know that is that we have an FU for our stress. That's the ultimate stress. In shear, that capacity is going to be 60% of your tension capacity. So Fy and Fu are always logged for the tensile capacity of a material. So we'll always have this 0.6 factor that appears with shear terms, and you'll see that throughout the code. We're also looking at net areas. So this is a net shear area. The AN stands for net, and the V stands for shear. Or a net tension area. Once again, AN stands for net, and the T stands for tension. The only term in here that kind of stands out is this UBS. That is the tension distribution factor, and it's almost always going to be equal to 1 for almost all cases. So down here, the commentary of the steel code is going to give you a bunch of cases where UBS is equal to 1. So for example, if I have tension here, this is a shear connection. Here's another type of shear connection. This is tension. It's tension pulling on the gusset plate here. All of these are going to have UBS equal to 1 because the tension is effectively uniform over the cross section. Now, if we have tension that's not uniform, then we're going to use a UBS factor of 0.5. So they only present one case where this can happen in the commentary. So let's say I have this shear connection of a beam. So I have force going down, and my reaction is going to be distributed between two lines of bolts, which means this section has less tension, and this section over here has more tension. So because my tension varies, we're going to adopt a UBS for this equal to 0.5. That might be a bit conservative, but it works out fine for most design. So we did the first one, just straight up rupture for everything. If you look at the second one, this one is the same. So we actually have rupture in tension. So we'll notice tension rupture is required for block shear. So that's identical. The only difference is that this is now going to be yielding. So we're going to be looking at Fy here and a gross area, hence why there's a G there. So gross area in shear. So the code implies that we could also have block shear failure if you have yielding that kind of goes around your bolts, if you will, and then a tension rupture to separate the two pieces. Last thing we need to mention for the capacity is our strength reduction factor if we're doing LRFD. So this is a rupture type failure, so we're going to have a strength reduction factor of 0.75 for block shear. So now we're ready to do a few examples, and we're going to start off with this double angle that we had seen from our first video. This thing is going to be in tension, so it's being pulled this way. And first we need to draw our block shear failure path. So it's going to go through all the bolts here, and it could go up or it could go down. But in this case, it's definitely going to go down. As we can see, the area down below those bolts is way less than the area above. So I don't really need to even consider the block shear going up. I know that's going to be higher capacity. So now we can see we have a shear side right here. This is going to be shear, and this is going to be my tension. And what I like to do first is I like to get all the lengths of my path. So this length here, we'll call this LGV. G stands for gross, and the V is going to stand for shear. So this is the length of my shear path. And we can see it's 1.5 inches plus 9 inches. So that's going to be 10.5 inches. So LGV is 10.5 inches. Now, if I want to look at a net length for this, I'm going to start with my 10.5 inches, and I'm going to subtract off. We have 1, 2, 3, 4.5, because I'm just going to go to the middle of that hole. So that's 4.5 diameters. So 4.5, and now I need to know the diameter of those holes. Well, it is a 3/4 inch diameter bolt. If we look in table J3.3, we'll find that a standard hole for a 3/4 inch bolt is 1/16 inch bigger. So that is a 13/16 inch hole. And then plus I'm going to add a damage zone on there, because when we put that hole through the steel, you're probably going to be damaging some of the steel around there. So that is going to line us up with a 7/8 inch. Note, if you're doing this in metric, typically a standard hole is about 2 millimeters bigger than the bolt diameter, and the damage zone we also assume is about 2 millimeters. So it works out to be about the same if you're doing it in metric, but instead of the 1/16 of an inch, you're going to use 2 millimeters. All right, so we found our diameter is 7/8, so we got 4.5 of them, so that's 4.5 times 7/8, and this value is going to be 6.5625 inches right there. So that's the length, the net length of my block shear path. Now let's look at our block shear tension path. This distance right here, I'm going to call that LGT. And we can see that this is 2.5 inches from the top down. That's just where I decided to put my bolt. That's a typical gauge length for these angles. So 1.5 inches down to the bottom. Therefore, my LGT is 1.5 inches. So if I want LNT, that's my net length, I need to subtract off whatever holes are there. And I'm going to just subtract off half of a hole diameter. So we can see essentially it's just the radius, because I'm always drawing my paths through the center of the hole. So this is going to be 1.5 inches minus a half of 7/8 of an inch. So this is 1.0625 inches for those two lengths. So now I got my net shear and my net tension lengths. We're also going to need the gross shear length as well. So now let's turn those lengths into areas. In order to do that, we're going to need to multiply that by the thickness of our material. So for example, if I want my gross shear area, we'll call that AGV. I'm going to take my length, which is 10.5 inches, and I'm going to multiply by the thickness that it has to break through. Well, this is an angle with a 1/2 inch thick leg, and it has to break through 2 legs. So I'll quick go back to see that. So these legs are 1/2 inch thick, and I got to break 2 of them, 1 here, 2 there. So therefore, this is going to be 2 legs times 1/2 inch. So this is obviously just 10.5 square inches now. And if I look at my net area in shear, that's going to be A and V. I'm just going to take my net length, which is 6.5625 inches, times the same thickness. So it's 2 legs and then 1/2 inch thick each. So this is obviously 6.5625 square inches. Now, if we go to tension, we never use the gross area in tension. So we're just going to X that out, not calculate it, but we do need that net area. So ANT is going to be my net tension area. Therefore, I need my net tension length, which we found was 1.0625 inches. And same as before, I have to break 2 legs of an angle times 1/2. And that 2 is just because we have this double angle situation, and it's 1/2 inch thick. So this is obviously 1.0625 square inches. Now I'm ready to apply my block shear equation, but first I need my material properties, ultimate and yield stress. We're dealing with A36 steel here, so I'm going to look that up in table 2-4, and I'm going to find that Fu is equal to 58 ASI, and Fy is equal to 36 ASI. So my Rn is going to be equal to 0.6 times Fu, which is 58 ASI, times my net area in shear, which was 6.5625 square inches, and plus our UBS factor is 1. It almost always is 1, except in very rare circumstances. If I had multiple rows of bolts in this tension connection, it would actually still be 1. So we don't really have to do anything with that. Multiply that by Fu again, so that's 58 KSI, and then ANT, my net tension area, is 1.0625 square inches. So this is about 290 kips. And now I need to calculate my second term right here. So that's equal to 0.6 times now 36 KSI, because I'm dealing with yield, times 10.5 square inches, because now I have to use my gross area instead of my net area. And I'm going to say plus, and this is all the same, so I'll just kind of use a ditto sign, just copy that down. It's the same term in both cases, and I'll find that this is 288 kips. So that, in fact, controls, because it is the lower of the two. And then I just need to apply a phi factor of it. So if we put a phi factor of 0.75 on that, we're going to find that the capacity of this is 216 kips for block shear. So if you remember from the previous video, our demand was 200 kips, so we're good. So the last thing I want to do is I want to very quickly go through one more example where we have to look at multiple paths to see which one controls. Because in this double angle, we really only had one option for our block shear path, but if you have multiple, you sometimes have to check to see which one will control. So we're going to look at this T connected to a plate once again. Let's say we have tension here and here, and I want to calculate the block shear capacity of this section. For the T shape, because we had that large stem right here that gives you a lot of tension area, effectively there's only one path that's worth checking, and that's this one right here. So that one will be fairly obvious and pretty straightforward. But for the plate, we could have multiple options. So we could have the classic U-shape one. We'll definitely want to check that. We might have a fracture going through both lines here and then going outwards, but it turns out we don't need to check that. Reason being is we know that this is a 4-inch gap right here, so this is 4 inches of tension. If I go to the outside, because this plate is 9 inches wide, 2.5 plus 2.5 inches is 5 inches total. 5 inches of a tension area is bigger than 4 inches of our tension area, so I know that this T-shaped block shear is not going to control. It just has more tension, but it has the same amount of shear as the U-shaped path that I'm looking at here. So the only other one I need to look at is this L-shaped path going in that direction right there. And of course, that's going to be identical to this path right here. The reason we need to check both of those is this has more tension, but less shear, because I only have one shear rupture along this line, but I have a larger tension area. So which one's going to control, I don't know until I calculate it out. So let's go ahead and do that. And we're going to start with the T. We can look up all of our T cross-sectional dimensions here in table 1-8. And the numbers that we're going to need specifically is this distance right here. This is BF, the width of the flange is going to be 8.05 inches. That's going to be a key number that we need to know. And then we also need to know the thickness of this flange, which is listed as TF in table 1-8, and that is 0.575 inches. Obviously, it's also going to give you dimensions for this stem. We're assuming the stem gives us so much area that we don't really need to worry about it, so we're just going to ignore that for now. Other thing that we're going to need is we need to know our hole diameters for our bolts. Now we're using 7/8 inch bolts in this case. The hole diameter, if we look in table J3.3, is going to be 15/16 of an inch. So that's 1/16 greater than the bolt diameter to make sure that it all fits. And then obviously we're going to add a 1/16 inch for damage to that, which gets us to a square 1-inch diameter hole that we'll be subtracting from our section. So let's draw our block shear path. Once again, we're going to have 2 tension paths in this case, and 2 shear paths. So here's my 2 shear paths, and then here's my 2 tension paths, and we just add them together. So they just strictly sum up. If we look at shear first, I have 2 of these, and it is 9 plus 1.75 inches long for each of them. So my gross shear area is 2 paths times 10.75 inches per path gets me 21.5 inches. Now I need to subtract off my hole diameters, and I have 1, 2, 3.5. So that's 3.5 on top, and then another 1, 2, 3.5 on bottom. So that's a total of 7 diameters. So 7. The diameter of a hole is 1 inch, accounting for the damage zone. So therefore, this length, the net length, is 14.5 inches. Multiply those by the thickness. In this case, we just literally multiply it by 0.575. That's all we need to do, because this plate is obviously 0.575 inches thick. And I'm already accounting for the fact that there's 2 paths here in my length. So I'm not going to multiply it by 2 again. I've already done that right here. So that gets us a gross and a net shear area. So now we can move on to tension. Tension, we need to find this distance right here. And so that is going to be 8.05 minus 4, and then divide that whole result by 2. So this is going to be 2.025 inches. And I need to multiply that by 2 again because I got 2 paths. So that brings me back up to 4.05 inches for the gross length, minus 1 inch. So essentially we have 1 hole diameter that I need to subtract from this case. There's a half hole diameter here and a half hole diameter here, which adds up to 1 hole diameter of 1 inch. So that gets me 3.05 inches. And therefore multiplying that by the thickness gets me 1.75 square inches. We'll look up our material properties. This T-shaped section is A992 steel, which has a yield of 50 KSI and an ultimate stress of 65 KSI. So now essentially we just plug in all of our areas. We got shear rupture, tension rupture, or shear yield and tension rupture, because we always have tension rupture. And we'll find the rupture case controls, multiply that point by 0.75, and we'll find that this is 329 kips of capacity. Now we have 2 paths to check for our plate. So let's look at path 1 for this plate. Path 1 we're going to assume is going to be this one right here. So it's the U-shaped path. I had defined this plate to be 0.75 inches thick. I just chose that for this particular example. So if we look at the length, once again, we have 2 paths. And the paths are still, this was 9 inches here, plus 1.75. So it's the same distance as we had before. So 10.75 per path times 2 paths. We still have 1, 2, 3.5. So 3.5 and another 1, 2, 3.5. So that's a total of 7 holes that I need to subtract out. Multiply that by the thickness to get my gross and net shear areas. So looks great. Tension in this case, this was just 4 inches here. So straight up, that is my gross length for tension. I got to subtract out half plus another half. So that's a full hole. So 1 times 1 inch multiply by the thickness. That gets me my net tension area. Plugging all those areas into the equation with our A36 steel properties. So this plate being A36 steel has a yield of 36 KSI, ultimate of 58 KSI. In this case, we see that the yielding plus tension rupture actually controls. So that means 479 would be the capacity there, times 0.75 gives us 359 kips of capacity. And now we need to check the other path. So once again, we don't know which of our two paths will control for this plate, so we just need to look at both of them. This path is going to go through one line of bolts in shear and then down to the far edge in tension. This shear looks basically identical to the previous example, except we only have one path, so it's just straight up 10.75 inches. And now I only have 3.5 holes because I got 1, 2, 3.5 that I need to subtract. I don't have to worry about any of these because my shear path doesn't go through them. So 3.5 times the hole diameter, and then multiplying all that by the thickness of 3/4 of an inch gets us the areas for shear. For tension, we just need to know the distances here. So this was 4 inches, and this is 2.5 inches. So the total length is 6.5 inches. We got right here. We're now going to subtract out 1.5 holes to get our net area. So that's what we're doing right here. And multiplying by the thickness to get a net tension area of 3.75 right there. Once again, plugging all those areas into our equations, we find again that this yielding one controls. So yielding on shear plus a tension rupture gets us 392 kips times a phi factor of 0.75 gives us a capacity of 294 kips. And it turns out that is the controlling capacity among all of these. So if I were to say my block shear capacity for this particular connection would be a failure of path 2 in this plate equal to 294 kips. So that is our overview of block shear. As always, I hope you learned something, and I will see you next time.